Hello everyone. Welcome to my YouTube channel on engineering mathematics. In this video, we are going to learn the definition and some of the properties of the special function called as beta function. So let us see first the definition of beta function. For any real numbers m, n greater than 0, we denote beta function of m, n by this notation beta of m, n, and is defined as an integral of x raised to m minus 1 into 1 minus x raised to n minus 1 dx over the limit 0 to 1. For example, beta of 5 comma 3 is equal to integral of x raised to 4 into 1 minus x square dx over the limit 0 to 1. Now let us see relation between beta and gamma function. In my previous video, we saw the definition and properties of gamma function. Link of that video is given in the description box. The relation between beta and gamma function is as follows. Beta of m, n is equal to gamma of m into gamma of n upon gamma of m plus n. For example, beta of 3, 4 is given by gamma of 3 into gamma of 4 upon gamma of 3 plus 4, that is gamma of 7. We accept this relation between beta and gamma function without proof, as the concepts required to understand the proof of this relation are not yet taught to you. Now let us proceed to learn some of the properties of beta function. The very first property that we are going to see is beta of m, n is equal to beta of n, m. To prove this, we first consider integral definition of beta of m, n. That is integral of x raised to m minus 1 into 1 minus x raised to n minus 1 dx over the limit 0 to 1. Now we substitute 1 minus x is equal to t. Therefore, x is equal to 1 minus t. Therefore, dx is equal to minus dt. Now let us see what will be the limits for t when limits for x were 0 and 1. For that, let's put x is equal to 0 in this. We see t is equal to 1, and when x is equal to 1, we see t becomes 0. Therefore, this integral now can be written as integral from 1 to 0 of x is 1 minus t. So x raised to m minus 1 becomes 1 minus t raised to m minus 1 into 1 minus x is t. So 1 minus x raised to n minus 1 becomes t raised to n minus 1, and dx is minus dt. So we put this minus sign outside the integral and we write dt over here. Now we swap these limits, then this minus sign will disappear. So now we have integral of 1 minus t raised to m minus 1 into t raised to n minus 1 dt over the limit 0 to 1. But this integral is nothing but beta of n, m. Therefore, we say beta of m, n is equal to beta of n, m. I hope you understood this property. Moving ahead for next property, beta of m, n is equal to twice integral of sine raised to 2m minus 1 theta into cos raised to 2n minus 1 theta d theta over the limit 0 to pi by 2. This definition of beta of m, n is also called as second form of beta function. To obtain this second form of beta function, one should substitute x is equal to sine square theta in the first form of beta function, that is integral of x raised to m minus 1 into 1 minus x raised to n minus 1 dx over the limit 0 to 1. So if we consider x is equal to sine square theta, then dx will be equal to 2 sine theta into cos theta into d theta. Now let us see what will be the limits for theta when limits for x are 0 and 1. For that, we put these limits of x in this statement. So when x is 0, theta will be 0, and when x is 1, theta will be pi by 2. So limits of theta will vary from 0 to pi by 2. Now we transform this integral. Therefore, beta of m comma n can be written as integral from 0 to pi by 2 of x raised to m minus 1 become sine square theta raised to m minus 1. 1 minus x, that is 1 minus sine square theta, is equal to cos square theta raised to n minus 1 into dx, that is 2 sine theta into cos theta d theta. Now let us simplify this. First of all, we'll take out this constant 2. Then this sine square theta raised to m minus 1 can be written as sine raised to 2m minus 2. Similarly, this cos square theta raised to n minus 1 can be written as cos theta raised to 2n minus 2. Then we add powers of this sine term and this sine. Similarly, this cosine term with this cosine term. So we get twice integral of sine raised to 2m minus 1 theta into cos raised to 2n minus 1 theta d theta over the limit 0 to pi by 2. This is second form of beta function. Let us go ahead for next property. Next we will prove that integration of sine raised to p theta into cos raised to q theta d theta over the limit 0 to pi by 2 can be given by half beta of p plus 1 by 2 comma q plus 1 by 2. To prove this statement, we will make use of previous property which says beta of m comma n is equal to twice integral of sine raised to 2m minus 1 theta into cos raised to 2n minus 1 theta d theta over the limit 0 to pi by 2. In this statement, we will put 2m minus 1 is equal to p and 2n minus 1 is equal to q. Therefore, m will become p plus 1 by 2 and n will become q plus 1 by 2. Now let us substitute values of this m and n on both the sides of this equation. So this beta of m comma n can be written as twice integral of sine raised to p theta into cos raised to q theta d theta over the limit 0 to pi by 2. Whereas this LHS now can be written as beta of m is p plus 1 by 2 and n is q plus 1 by 2. And then finally, we take this 2 on the other side to prove this statement. I hope you understood this proof. Let us see use of this property. Using this property, one can write value of the integral of sine cube theta into cos raised to 5 theta d theta over the limit 0 to pi by 2 as half beta of p plus 1 by 2, here p is 3, so it will be 4 by 2, comma q plus 1 by 2, here q is 5, so it will be 5 plus 1, that is 6 by 2. Then using beta gamma relation, you can simplify this RHS part. Let us see next property. Next we will see value of gamma of half can be given by root of pi. To prove this statement, we will make use of previous property which states that value of the integral sine raised to p theta into cos raised to q theta d theta over the limit 0 to pi by 2 is given by half beta p plus 1 by 2 comma q plus 1 by 2. In this statement, we will put p and q both equal to 0. So let us see what will happen when we substitute p and q is equal to 0. This LHS becomes half beta of half comma half, whereas RHS becomes integral of sine raised to 0 theta into cos raised to 0 theta d theta over the limit 0 to pi by 2. Now in the left hand side, we will make use of beta gamma relation and we write beta of half comma half as gamma half into gamma half upon gamma of half plus half, that is gamma of 1. Whereas this RHS can be written as integral of d theta over the limit 0 to pi by 2. Next we evaluate this RHS integral. We get value of the integral is theta over the limit 0 to pi by 2. After substituting those limits, we get only pi by 2 on the right hand side. like this. Now finally, this 2 and this 2 will get cancelled, and we will left with gamma of half square is equal to pi. Then taking square root on both the sides, we can say gamma of half is equal to root pi. I hope you understood this property. Let us go ahead for next property. Next we will prove that integral of x raised to m minus 1 upon 1 plus x raised to m plus n dx over the limit 0 to infinity is also equal to beta of m comma n. You can consider this statement as third form of beta function. To prove this statement, one has to put x is equal to tan square theta in the left hand side. So dx will become 2 into tan theta into sec square theta d theta. Now we see the change in limits. When x is equal to 0, theta will also be equal to 0. Whereas when x is equal to infinity, theta will be pi by 2. Now let us transform this integral. So this integral now will become integral from 0 to pi by 2 of x raised to m minus 1 can be written as tan square theta raised to m minus 1, that is tan raised to 2m minus 2 theta upon 1 plus x raised to m plus n can be written as 1 plus tan square theta raised to m plus n into dx, that is 2 tan theta into sec square theta d theta. Let us simplify this right hand side. 1 plus tan square theta is sec square theta. So 1 plus tan square theta raised to m plus n is sec raised to 2m plus 2n theta. We also have sec term here. So to multiply these two terms, we have to add their degrees. So in the denominator we have sec theta raised to 2m plus 2n minus 2. Whereas the numerator becomes tan raised to 2m minus 2 theta into tan theta, that is tan raised to 2m minus 1 theta. Next we write this tan theta as sin theta upon cos theta and this sec theta as 1 upon cos theta. That cos theta term will go in the numerator. Then we finally take this cos theta term in the numerator. So this cosine will have degree 2m plus 2n minus 2 minus 2m plus 1. Let us carry forward this statement. Now here this 2m and minus 2m will get cancelled. Minus 2 plus 1 will become minus 1. So this cosine will have degree 2n minus 1. Now observe this RHS part. It is nothing but second form of beta function. So we write this as beta of m comma n. Hence this property is proved. I hope you understood this proof. Now next we see the duplication formula, which states that 2 raised to 2m minus 1 into gamma of m into gamma of m plus half is equal to root pi into gamma of 2m. Let's prove this. We know that integral of sin raised to p theta into cos raised to q theta d theta over the limit 0 to pi by 2 is given by half beta of p plus 1 by 2 comma q plus 1 by 2. In this statement, we will put p is equal to q. We get left hand side as integral of sin raised to p theta into cos raised to q theta d theta over the limit 0 to pi by 2. Whereas right hand side becomes half beta of p plus 1 by 2 comma p plus 1 by 2. Now let us recall trigonometric identity, which states sin 2 theta as 2 sin theta into cos theta. We do have sin theta into cos theta here. Only 2 is missing. So we multiply and divide here by 2 raised to p to get 1 by 2 raised to p into integral of sin of 2 theta whole raised to p d theta over the limit 0 to pi by 2. Whereas this right hand side can be written as half gamma p plus 1 by 2 into gamma p plus 1 by 2 divided by gamma of p plus 1 by 2 plus p plus 1 by 2, that is just gamma of p plus 1. This was obtained using a relation between beta and gamma functions. Now let us concentrate on this left hand side integral. We will evaluate it by using substitution technique. Before that, we label this statement as 1. Now we put 2 theta is equal to t in this left hand side integral. So d theta will be dt by 2. Let us see the change in limits. When theta is 0, t will also become 0. But when theta is pi by 2, t will become pi. Now let's transform this integral. So this integral will now become 1 by 2 raised to p into integral from 0 to pi of sine raised to p t dt by 2. Let us carry forward this statement. Now note that since sine of pi minus t is sine t, we can write this integral, which is from 0 to pi, as twice integral from 0 to pi by 2 of sine raised to pt dt. We are taking out this 2, so this 1 by 2 raised to p become 1 by 2 raised to p plus 1. Now this 2 and this degree 1 will get cancelled. So we will left with 1 by 2 raised to p into integral of sine raised to pt into dt over the limit 0 to pi by 2. Since cos raised to 0 t is 1, so we can put that cos raised to 0 t over here. Now using one of the property of beta function, this integral can be written as half beta of p plus 1 by 2 comma 0 plus 1 by 2, that is just 1 by 2. Now using beta gamma relation, beta of p plus 1 by 2 comma half can be written as gamma p plus 1 by 2 into gamma 1 by 2 divided by gamma p plus 1 by 2 plus 1 by 2, that is gamma p plus 2 by 2. We label this as 2. Now let us recall equation number 1, which states that value of this integral is half into gamma p plus 1 by 2 the whole square upon gamma p plus 1. But note that we just proved that value of this integral is 1 by 2 raised to p into half gamma p plus 1 by 2 into gamma of half upon gamma of p plus 2 by 2. So let us substitute value of this integral as this. So we get this statement. Now we have to simplify this to prove the duplication formula. Let us carry forward that statement. Here this half and this half will get cancelled. So we are left with 1 by 2 raised to p. This gamma of half can be written as root pi. This gamma p plus 1 by 2 will get cancelled with one of the gamma p plus 1 by 2 on the other side. So on left hand side, we will left with 1 by 2 raised to p into root pi upon gamma p plus 2 by 2 is equal to gamma p plus 1 by 2 upon gamma p plus 1. Now remember our substitution in one of the property of beta function, that was 2m minus 1 is equal to p. So here after substituting p is equal to 2m minus 1, we can have root pi upon 2 raised to 2m minus 1 upon gamma m plus half is equal to gamma m upon gamma 2m. You can pause the video and check this calculation. Now we simply cross multiply these elements to get 2 raised to 2m minus 1 into gamma m into gamma m plus half is equal to root pi into gamma 2m. Hence the duplication formula. I hope you understood these properties of beta functions. In my next session, we will see examples on evaluation of integrals with the help of beta function and its properties. Till then, thank you all of you. Thank you for watching this video. Please subscribe my YouTube channel and press the bell icon to get updates about my new videos.